Hey, what's up, guys? So here we are back again for some more mechanical engineering theory on the optimal start math playground, predicting the optimal amount of time to start an HVAC system, which we've been talking about a lot here. So we're about halfway through the course. Read the paper in the repo. This is the research paper that we're going off of. And mostly we're talking about, like, before the building starts, we get that delta temperature that the building needs to warm up or cool down to, the occupied zone temp set point, and the amount of minutes that it takes to reach that zone, to recover the zone. And then the researchers defined in this paper, they have a lot of different math models to predict minutes, which were playing around in Python to run these different models. So in my Niagara Program Object here, I've just checked on this morning, and so this is something where before I added the bonus days to the course, I put in models 3 and 4, which are defined in the paper, where we've been looking at this week with we're doing the linear regression, matrix algebra from scratch, multiple linear regression, the matrix algebra required to fit the model, and then all the dot product information that's running in here. So, and for whatever reason, there's not a lot of data, and the temperature operating at this building has been kind of mild. As you can see, it's 51 degrees outside in this building, the east coast of the United States, January, so there hasn't been a ton of need for optimal start, but it's been running, and for whatever reason, this model 2 has the best average squared error. So my block is actually using model 2 at the moment. So I'm getting the best performance out of model 2. So we're only halfway through the course right now, and maybe as you know, maybe when I finish the course, maybe it'll take another month or so, I don't know, but maybe a different model will start predicting better and have the best squared error. So we'll just save the screenshot for a little bit later in the future. But model 0, that was the linear model, degree per minute. Model 1 was what was model 1? Model 1 was the quadratic regression. So that was the white paper said to take the delta temperature and make a quadratic regression out of the data. So at the moment, this model has 40 different runs. So there's an array of data. So like we're capturing that critical minutes required to recover the zone, then also the delta temperature here, which is this 73. Here's our zone temp. So this is the delta temperature that it takes to get that. So we're holding this data in an array is our delta temperature, and the amount of minutes, and then each one of these different models has a couple different different ways of predicting minutes. And then currently our average squared error, model 2 is the best. Model 1 was the quadratic regression of just minutes and delta temperature. Model 2 was linear degree per minute and then a weather factor, so we also incorporated weather. That's why our outdoor air temperature sensor is wired in here. And then also model 3, that was the multiple linear regression, which we've been talking about, all the matrix algebra by hand. And model 4 we haven't got to yet, and that was the first order physics driven iterative type of model. So getting the best performance out of model 2. So let's check back on this. But the last run that the last run actually took 22 minutes for this zone to warm up. I don't have the data what the zone temperature was at that time, but it was probably like low 60s, so maybe almost a 10-degree delta. So it took 22 minutes to warm up that zone, and our best model predicted 20 minutes, 20.72. So yeah, kind of cool. So I'm dying to see like what these other, once we have, I bet there's only like 5 days of data that the block is holding right now, and we can hold up to 40. So who knows? Let's check it out in the future. Okay, so I'm going to try and go over this. We're on day 6. I know this stuff is kind of tough, and could spend a whole college semester on matrix algebra alone, and then what goes on in the mechanical engineering side of things. So we're kind of breezing over this real fast. So day 6, conditioning and stability. Why is regression can become numerically unstable? If features are correlated or have very large X transpose X, it becomes ill-conditioned. Small noise correlates to large coefficient swings. That's why we are calculating the best model with the average squared error and not just error. Stability techniques, scale the inputs, add ridge term. I'm kind of unfamiliar with this. So ridge regression, I'm actually not really sure. I know that I don't think any of my college courses cover this, but I have seen ridge regression a lot in machine learning. I may as well get ChatGPT fired up here for some, let's see, we were on, where were we? I think we're on this chat. Quite a few different chats here. So, so this is just smoothing factor. It's interesting. I don't know what this would do. I don't think it'll do anything. Let's just delete this. Yeah, because we don't have, I wonder if we could weave it into our code base, though. I don't think so. Nor do I have the time. That was our code base from yesterday. So, micro exercise, scale delta temperature and fit model 3. Kind of curious. Scale delta temperature and refit model 3. I don't know where it would be. Well, let's see. Maybe I'll ask ChatGPT. How to utilize this in day 6 of the, whoops. Sorry, jumping around too much. You can use the determinant 3 in day 6 for the model's normal equation, matrix X transpose X, or X transpose X plus this new thing right here, the ridge. If X transpose X is 0, matrix is singular, you can't solve uniquely. You'll hit a 0 pivot like we talked about yesterday. If X transpose X is tiny, almost singular, solutions become noisy and unstable. Adding the ridge makes determinant non-zero and stable to solve. So that's ridge regression in normal equation form. So determinant X transpose X before adding the ridge to show the ridge is fixing. Huh, interesting. So that's what they did here. Add lambda lambda to diagonal. So it's just smoothing this out, I think. Shoot, I think we needed all that code. Dang. Okay, so we need this guy. And then we're factoring in this guy. Alright, here we go. So now we have our determinant, compute determinant for a 3x3 matrix using cofactor expression. Solve for A, X equals B for a 3x3 system using forward elimination and back substitution, pure Python libraries. Wow. Solve ridge. Oh, I wish I had a whole college semester for this, but looks kind of interesting. Determinant. So, hey, looks kind of interesting, I guess. Compare the ridge 0 versus 1. Okay, so it did that here. So that's our lambda, or our coefficients. Slightly different, I guess. I don't know. Add ridge logic to your solver. Okay, so we did that already. And explain ridge regression in plain English. Okay, so would be using the lambda and solvers to smooth out the end product. I know I'm kind of cheating here, and definitely definitely a little bit of faking it here. So seems kind of interesting. So small ridge, gentle smoothing, large ridge. Well, ridge regression is a data science version of good control tuning. I like that. Alright, so maybe we can do day 7 right away if we got enough time. Build a Model 3 regression from scratch. No libraries. I have this. So due to the time that we all don't have in the working day, I might just say, hey, it's done. So let's check it out. Well, then we can move on to Model 4 tomorrow. So PNNL Model 3, manual matrix library, pure Python, no NumPy, no scikit-learn, just raw math for learning purposes. So this is, like I was saying, in the Java, the program objects, like the block is holding this data in that 40 days window. So we have delta temperature. Oh yeah, this one has a weather factor, and then that's our minutes it took to condition the zone, where before in the screenshot I was showing like 21 point something minutes. So this is just fake data, but it could look like something like that. So we have so it looks like our code is going through here, and it's appending like a new Python list here is our matrix multiplication. Manually calculate X transpose times X. That results in 3 by 3 matrices. So that's our matrix. This is our manually calculate X transpose Y, 3 by 1. So that calculates that manually. Here's our determinant. Calculate the determinant of a 3 by 3 matrix. Rule of Sarius. Solve the normal equation. And yeah, these are our parameters that the paper calls for. So if you look in the paper, so that's alpha 3D, alpha 3A, alpha 3B. So this would be our coefficient for delta time, times the weather factor, and then this is our intercept for the multiple regression. And in our paper, that is this right here. There's our alpha 3D, alpha 3B right here. There's like with the weather factor, and then this is just our delta temperature, our temperature set point minus the zone temperature. So that's it. So if we say Python model 3 math libraries, this is how our multiple regression model gets fit. Pretty crazy, the math that we've been talking about all week. And then those are our coefficients, and then we plug in our data into the equation and we calculate 26 minutes. Pretty cool. And the paper does say that this model does, they think that predicts the best. So we'll see over time if I get that same thing. Dying to see that. But that's it. And then model 3. So this is one with using the math libraries. It's interesting that it takes a little longer for it to fit. Oh yeah, I think we talked about this earlier because the scikit-learn, running the linear regression, and also like this code makes this neat little plot for this 3D. So yeah, it's pretty cool. So that with the fancy math libraries, they get the same results. 26.8 minutes. So pretty cool. Like the code, like when you don't do everything by hand, which you wouldn't do if you had these math libraries available, is much cleaner. Like it's just like all of this stuff is running behind the scenes where someone coded this up and they put that inside of the inside of the scikit-learn and NumPy libraries. So yeah, pretty neat. I think very smart people make these math libraries and these equations defined in research. I would never be able to come up with this stuff, but I'm very thankful for not only all these people in AI to help me implement it on the building automation system, and also for all of you guys, if there's anyone even watching this. And I also want to point out that I have this is next. Hopefully this summertime I'll be able to get to this in time, but what I want to do is another 50-day on brick models, data modeling, so graph theory, RDF. So this is coming. There's some Sparkle queries by hand, so I put ChatGPT to the test to make another 50-day tutorial. So it's coming, 57-day. So this one's coming hopefully in the summer of 2026. So until then, happy HVAC minute modeling, and I will catch you guys on the next one. Talk to you later.